Sybase, if you can see me, optimized for time series. This is not the most up-to-date solution. That was roughly until 2010, when it was widely used. Then a very interesting time series database solution came into play, which was called, and is still called, and we are going to discuss it today, KDB Plus, with a query language called Q, which really set a very high standard in terms of performance. I would say the ease of use, flexibility, and in general, the suitability to financial applications. KDB Plus is a very expensive commercial solution. You can request from the company, which is a technology provider for KDB Plus. The company is called kx.com. I encourage you to visit the website of the company. You can request evaluation versions of KDB Plus. There is a 64-bit Linux version and others. macOS is available, others are available, and 32-bit. Well, obviously, a 32-bit version is not really a high-performance database, because obviously the data size is limited by the number of addressable records, which is 4 giga records in this case. So it is okay for learning KDB+, but it is not even okay for high performance evaluation, let alone it is not sufficient for production use. You can get a free version in 64 bits, but it is delivered as a software as a service. So it requires a permanent internet connection, and basically the company measures the amount of time, the amount of CPU usage for your KDB session, and can discontinue your session in case if excessive use is detected. Commercial prices, as far as I remember, maybe they're different nowadays, but they start from 25K per CPU. So the price is based on how many CPUs in your shared, in your SMP symmetric multiprocessor setup you would be using. If you're on a host with, let's say, 10 or 20 processors, then the cost is scaled accordingly. So 25K per CPU, and moreover, it is not a one-off license, it is an annual one. So 25K per CPU per year, which is arguably quite expensive. And for a long time, there are no open source alternatives to KDB plus Q. You could use some poor man's substitutes. So for example, if you really optimize the database backend very carefully, in particular your insert operations and the engine itself, then you could get more or less reasonable insert performance from even MySQL. But this is definitely not a column-oriented, not a time series database. So running, for example, any digital signal processing algorithms over MySQL wouldn't be possible. Well, it would be, but you would need to do it in your user space, which is hugely suboptimal for time series database. Nowadays, very recently, in the past few years, open source alternatives, or let's say quasi-open source alternatives to KDB plus Q, they started to emerge. One of the possible alternatives is Amazon Redshift, which you can use over Amazon clouds. And the other one, by the way, you are encouraged to have a look at all these solutions. So you can download KDB Plus. You can use using software as a service Amazon Redshift. In particular, using Redshift is a good idea if your data itself are stored in the cloud, and then it is a cloud service which integrates very well with Amazon set of services, and that's why you can use it in a relatively easy way. So, for example, if your financial analytics is cloud-centric, then it is probably a very good solution. There are other solutions, for example, from Yandex, which could be used to that end as open source time series databases. But today, we are going to discuss in more detail. We're going to discuss KDB plus Q. So I will give you some kind of hands-on tutorial and explain why KDB plus Q is a good idea, why it might still be the standard, the state of the art for time series databases nowadays. All high performance financial time series applications run by major international investment banks, let's say JP Morgan, Citi, UBS, the Royal Bank of Scotland, others are nowadays based on KDB plus Q. So it is a very good idea to at least familiarize ourselves with this technology. So you know such a technology exists and you have an idea about how to use it. Maybe if you get interested, you would go further with regards to that. Before we starting on to explore the KDB Plus, or more precisely the Q language, I would like to ask you, how familiar are you with functional programming? Not quite. Or to some extent you are. Tell me, please. Don't be shy. You can turn on your microphone and say, have you seen functional programming? Not quite. But you know what it is all about, actually. It is a programming paradigm in which your computation is structured as one big function mapping your inputs into the output. And this big function is comprised of subfunctions, which are comprised of subfunctions and so on. The functions can be recursive. Moreover, the functions could be mutually recursive. Function A calls B, B calls A, until if the computation terminates. So the whole computation is structured as a big tree of function calls. And the major data type, which is processed by functions, by those functions in the functional programming paradigm, is the type of list. The list can be of any data types, of elementary types like integers or floating points or characters, or there could be record types, which are sometimes also called tuples. There are other types, well, for example, variant records, which are sometimes called algebraic data types in functional programming. This is a very, in fact, very powerful paradigm. It is not just of academic interest. It is very widely used nowadays, and the main programming languages implementing the functional programming paradigm are the following. No doubt you have heard about at least some of them, or maybe you have seen some of them. Haskell, languages of ML family, the most, I would say, venerable one of them is standard ML. More modern OCaml. Yet another one is, by the way, F#, which belongs to the Microsoft.NET software suite. These are two major families. There are some others. So, for example, Scala, which you have probably seen, and so on. But I would say still nowadays Haskell and possibly OCaml, they are primary functional languages in very heavy, not only academic, but industrial use nowadays. And they are also used, for example, in computational finance very much. Q, which we are considering here in this lecture, belongs to the same type of languages. Q is a functional language. So everything is a function, and it operates on typical functional data structures, which are tuples or lists. Q has a very interesting history. Long time ago, back in 1950s, 1960s, there was a programming language which was called APL. APL simply stands for a programming language, just a programming language. So, which was picked up by IBM and at some point became one of the languages heavily supported by IBM. This is as an ancestor of Q. It was used for, primarily at that time, interestingly, for mathematical computations. Obviously, the first language developed for mathematical computations was Fortran, if you remember, at about that time as well. But APL provided a very concise, terse syntax, and because it was already functional at that time, it allowed us to provide very easy, highly expressible programming language constructs, and it was simply much easier to write, especially to represent complex computational logic, than it would be by programming, let's say, loops and conditionals in Fortran. But it was so expressive, so concise, so terse, that it was called write once, never read back, programming language. And this is indeed a problem. If your programming language is very highly expressive, it is quite likely that it is easy to write, but very difficult to read back and maintain, especially if your programming code is poorly commented, if you do not maintain any documentation and so on. So to some extent, Q is also write once, never read back. Well, not quite, but improper use of some Q constructs may present readability and maintainability problems. So please be aware of that. Please do not follow obscure practices, but if you use it in a reasonable way, then it is perfectly okay, and it is really a good technology to begin with for the financial time series process. What is also important, I would like to draw up a certain diagram for you. So how could, in general, financial time series be processed using more conventional technologies? So what would happen? And first of all, there is a database, so conventional approach. In the conventional approach, there is a database where your time series reside. Okay. Then what could you do with this database? First of all, there is probably some built-in procedures of your database, very much like those implemented in, let's say, Oracle or Microsoft SQL Server or even Postgres. So there is a built-in language of procedures, right? So some logic, which of course interacts with this, closely interacts with the database content. And some logic can be implemented in terms of this language, but some logic cannot. So then there is also some external, for example, you know, if it is Oracle, suppose that, for example, this is Oracle. Then you know that this built-in language of stored procedures in Oracle is called how? What the name? Anyone have seen it? Please don't be shy. You know what you don't remember. It's called PLSQL. I'm absolutely sure you have seen it. Okay. Some logic can be implemented inside the database using this PLSQL language. Some logic is implemented outside in a general purpose programming language. What would it be in this case? Let's say it is Java. So this is inside the database, Java is outside. So then your Java needs to interface to the database somehow. The compatibility layer between your Java application and, let's say, an Oracle database is either a native driver or it is what? Java Object Database Connectivity, JODBC. That's the general way of how you interact with the database. And interacting with the database, you interact with the built-in stored, with the stored, I would say, with the stored procedures. Okay. Then, so part of your computations are here. Then suppose that your data are to be sent over the network. In order to do this, you need to implement yet another extension, which is serialization and deserialization of data. So we have already quite a lot of different components here. In particular, there is a question of maybe and maybe something else. If, for example, in addition to storing your data in a database, you would like to do some kind of file I/O with your data, then you probably use yet another serialization, which is not the same as used over the internet, but for example, you use, I don't know, maybe XML-based representation. Well, basically, your application logic and your data formats are really manifold here. Part of your application logic is here in Java. Part of the application logic is in stored procedures. You have one serialization for the internet transfers, another serialization perhaps for file I/O. Maybe yet another one would be for data visualization, and so on, which is quite, I would say, tedious, cumbersome, inconvenient, error-prone, tedious to develop, and so on and so on. So you see that those data-intensive applications are in fact involve much more than a simple database and require a significant effort to develop. So what KDB plus Q tries to do is to implement everything under one hood. So basically you have your Q as a query language, which is by itself a general purpose programming language, which allows you to implement any business logic you would like. It is sufficiently versatile functional language backed by, in general, either file storage or KDB plus database. We are primarily interested in the Q language in this case, because it allows you to specify both actually your data model and your data processing applications. So let's begin. In my screen, you see the Q prompt. I have installed that 64-bit version of Q on my Linux machine. I hope you can see it. So let's familiarize ourselves with the typical objects in the Q language. Okay, integer constants. Obviously, we understand what it is. Floating point constants. Yes. Obviously, very simple arithmetic. Single equality means comparison for equality. Zero B means obviously false, as you can imagine. Dates and time. That's the date. The date is as convenient and conventional in finance, is simply represented as an integral count of days since the epoch. And the epoch is the first day of our new millennium. So 1st of January 2000, not 2001. That's the day 1. Time. Time is represented as nanoseconds from the midnight. So, for example, 1744, 50, and up to 9 nanosecond digits. Okay. Strings are represented with left ticks, and they're actually atoms. So each string is immutable and represents an atom, an atomic object in Q. Now, the basic, so everything is simple about the elementary data types. There is an assignment operator, and because it is a functional language, actually you should treat this assignment as a definition, although your variables are in fact reassignable, unlike most functional languages. The assignment operator is given by the colon. So simply, let's say A42, assign the value 42 to A. The main data aggregate data type is the list, and the lists are allowed to be heterogeneous. So they are enclosed in parentheses, separated by semicolons. So for example, you can do something like 1, 1.1, and maybe a string 1, which is a valid heterogeneous list in Q. But you can also create homogeneous lists in Q. In that case, there is some syntactic sugar which simplifies you to do so. So for example, if instead of this list, you create a list of homogeneous elements of the same dynamically determined type, so all of them are just integers, then you see that the list is printed differently, because it is a more compactly represented in storage and also in display homogeneous list. Moreover, in this case, the parentheses and the semicolons are not really required. So the same as just juxtaposition space separated values are actually okay in that case. But there are obviously some, as customary with any functional language, list generating functions. So the most useful function is, for example, to generate a list of values of integers from 0 to n minus 1, which is called till 10. Values from 0 to 9. There are list operations. So if you do addition 1 plus till 10, then it is important that all expressions in Q are evaluated right to left. So first, this function till 10 is evaluated. Well, the argument 10 is evaluated for itself. The function till is applied to produce a list, which we have seen above, from 0 to 9, and then 1 is added to each and every element of the list. So then we really get elements from 1 to 10. This can be mixed with assignment. So we can say A, for example, 1 plus till 10, spaces are only needed where they are really needed. It's up to you whether you introduce them in your program or not. Then A, this list. What is also interesting about this is that you can, there are some other functions. So for example, comma simply means list concatenation. 1, 2, 3, comma 5, 6 should produce a concatenated list, and it is indeed the case. Then there is an element which is called, which is simply hash, and this hash takes a given number of elements. It is a binary operator, takes actually returns a list with the given number of elements from the beginning of the given list. So once again, A is a list from 1 to 10. If we say 1A, it would return the list of length 1 from the beginning of A. Indeed. If we say 2A, then we get a list 1, 2, and so on. If we select the value of the first argument longer than the list, the length of the list, it would start over from the beginning. 100A produce a repetition, as you can see, which means that you can actually very easily create constant lists with the constant element of a given length. So for example, you can create a list containing 5 elements, each of them equal to, let's say, 42. In this case, first of all, the second argument is lifted to a list, and then this list is repeated over 5 times because you are taking 5 elements and the list only has 1 element. It is also possible to access elements of the list by index. So if again we have our A, then for example A of 0, the 0 based is obviously 1. So that's about lists. Now a very interesting thing. We want to define, it is a functional language, and we want to define functions in Q. Functions are lambda expressions. Okay, you are not, as we say, that much familiar with functional programming, but the question is, have you ever seen lambdas somewhere?
Yes, we had it during our theoretical computer science course.
Wonderful. But if you had your theoretical computer science course, then you're pretty much familiar with functional programming. So you know what the lambda is. Let's define.
Of course.
Lambda. Yes. So let's define a lambda. Lambda is in general defined like that. So first of all, the list of arguments, and then the operation, which is, let's say, x times x. That's a lambda. By itself, this lambda is not very much useful. But if you apply this lambda, very much like a lambda application is done in lambda calculus, which you have seen in your theoretical computer science course, then you probably can guess what the result is, as we expected. All right. Moreover, you can, of course, the lambda by itself is an unnamed function, but you can assign this lambda to a variable. And then SQ itself is a functional lambda object, which you can apply to an argument. It works. Now, even the list of arguments is not important always. You can create functions with 1, 2, or 3 arguments in Q with the default values x, y, and z. In that case, specifying them in square brackets is not even required. So simply x plus y applied to 1 and 2 should work. Not quite. Because, why do you think? X times x was not fully valid. X times x applied to 3 works. X plus y applied to arguments 1 and 2 did not quite work. Never mind. We'll investigate why not. What if we do it if we add extra brackets? So x plus y applied to one function, to one value 1, take a lambda, x plus y applied to 1, and then applied to 2. Yes, that's fine. So in this case, parentheses are indeed needed. Okay. Oh, that works. By the way, this partial application, how is it called in theoretical computer science? You remember the term? When a function of 2 arguments is applied to one argument, one value, to produce a function of 1 argument, which can then be applied on its own. You remember what it is?
Beta reduction.
Carried functions. Carried functions. Okay. Then functions on lists, for example, because in many cases, well, in most cases, what our functions would do is to process lists in Q or in any other functional language. You remember from your theoretical computer science that there is an operation which is called fold, for example, on a list. All right? Do you remember what the fold is? What we want to do? We want, for example, to take a list and to sum up all elements of the list. This is an example of a fold. The fold takes a function. In this case, it is just the plus operator. And the plus operator operates on the current element of the list and the cumulative sum. So it is a function of 2 arguments. The initial value is the second argument, which is 0 if we do the summation, and the list itself. So for example, if you want to sum up the lists in the list elements in Q, you can do something similar to that. So the initial value of the sum is 0. Then we apply the operator plus, but we need to lift this operator plus so that it is really acting as the accumulator update in a fold. In this case, it is to be followed by so-called adverb in Q, which is slash, and applied to the list. For example, I think even this should work. Yes. This produces a sum of all values from 0 to 9, as you can check. So, do you like this style? What's better, to write this type of expression or to write a loop as in any conventional programming language, or to write maybe a recursive function or a fold in a functional language using your lambda calculus? What do you like? Till 10 producing a list and then summing up this list. Moreover, it is not even necessary to implement the initial value. In the following situation, the initial value would be guessed because it is a summation as a correct one, and obviously not to start with 0, we'll do 1 plus till 100. Yes, that's the right one. Okay. Obviously, you know, there are also some shortcuts, so you don't need to write this. This can be replaced by a built-in function sum in Q, which would have exactly the same result. So instead of using the slash adverb and folding delete this way, you can simply do sum of, you see, no brackets, no parentheses are required. Sum of 1 plus till 100. Till 100 produces a list of 100 elements long from 0 to 99. Then you move it to a list from 1 to 100 by adding 1. Then you sum it up, and you get exactly the same result. Okay. There is a maximum and minimum operations, which you can first of all apply on 2 elements. Guess the vertical bar. What is it? Is it a maximum or minimum? What do you think? Just from a simple logical standpoint. That's a max, very much like logical disjunction. Yes. Whereas ampersand stands for the minimum. Obviously, you can do a similar thing to find the minimum of the list by applying ampersand followed by the adverb, but there are also functions, for example, min and max by themselves. So for example, max 20, 21, 13, 10 should give it 21 as expected. Fine. Now let's do something little bit less trivial. We'll compute Fibonacci numbers in Q. So first of all, we will produce the whole list of Fibonacci numbers of a given length. So initially, this is 1 and 1, right? So let us define F0, for example, to be a list of 1 and 1. Why not? Now, what do? We take a sum. How do Fibonacci numbers define? If we have already a sequence of Fibonacci numbers, then we take the last two numbers, sum them up, and produce yet another element. You remember there was a hash operator in order to take the initial n numbers, but if n is negative, then you can take the last two elements from the list. So if I say -2 applied to f0, well, this is going to be 1 and 1. So if you do f0 followed by sum of -2, which means two trailing elements of f0, you now got the same 1, 1, and 2. You got the third Fibonacci numbers. Obviously, if you repeat this, you will get exactly the same result. Try assign this to f0. So f0 is the previous list followed by the sum of the last two elements of f0. Once again. Oh, better. You see? Oh, sorry, I didn't assign it. Once again. Should we get 5? Yes. And so on. But why stop here? So basically, what we would like to do, we would like to construct a function which takes an argument, supposedly a list, taking two last elements of the list, summing it up, and appending to the list. This is very simple. Take an argument x, and returning and concatenating it with the sum, x is implicit in this case, sum of -2 elements of x itself. That's a lambda. So if we apply now this function to our current f0, we got yet another element, and so on. Okay, we already have a function abstraction. Now I would like to introduce a high order function which takes this function and repeats its application to its own output over and over and over again. And such a function does exist. So the syntax is the following. So for example, take the number of applications 10, then our coveted function which we have just developed, which appends the sum of the last two elements of a list to the list. Then our lifting to a fold. You remember once again this adverb slash and the initial list. And we got 10 Fibonacci numbers. Let's get 20 Fibonacci numbers. Okay. Would it be able to compute 100 Fibonacci numbers? Or it would crash? Oh, it's okay. We don't see them, but they do exist. Let's see the last one. To see the last one, we would, what do? We compute it, and then we select the last element. We can do it that way, for example, of 99. Oh, yes. we can use, let's say, starting from 99, apply to the result of this computation. 99 hash. Oh no, that's the length of 99 starting from 1. Sorry, it wouldn't work. But this one does. Okay. So we already have a very nice example of using high order functions in Q. But now we are going to use it even to a greater power. From your mathematical analysis, from calculus, do you remember a root finding method, which is called Newton's method for finding roots of equations? Do you remember anything like that? No? It's easy if you tell rather than type in the chat. Okay, let's have a look. Suppose that we want to solve an equation. Newton, actually it is a Newton-Raphson, I think, method. Or Newton. Newton's root finding method. We want to solve an equation. F of x equals to, let's say, 0. Suppose that there is a certain function x, f of x, and we would like to find the root. Here the root. We have some initial approximation x0 for our root. What do we do? You remember what? We produce a tangential line and we find its intersection point with the x-axis. From that point, we compute the next value, so that would be x1. We compute the next value of our function, find the intersection point, and so on and so on. And this sequence, under some genericity conditions, would converge to the actual root. Not always, but there are some conditions for convergence. So, okay, if this is x0, this is obviously f of x0, correct? So what is the x1 then? You know that the tangent of our angle is precisely the derivative, because it is a tangential line here, the derivative of our function f of x in the point x0, which means, so this side of the triangle is precisely f of x0, this one is x0 minus x1 in this case. So f of x0 in this situation divided by x0 minus x1 equals to the derivative of our function f in the point x0. If we start from the other side, it would be effectively the same type of equation. So it is sufficient to consider only one case. Therefore, x1 equals to x0 minus f of x0 divided by f prime of x0. Or in general, we do multiple iterations from 0 to 1, from 1 so on, xi equals to xi minus 1 minus f of xi minus 1 divided by f prime of xi minus 1. This process for I, 1, 2, and so on. X0 is to be given. This process is called Newton iterations. Okay. Let us implement same method of Newton iterations to find roots of equations in Q. We will simplify our problem. So we will consider functions of the form f of x equals to x to the power n minus, for example, minus y. Obviously, the root of this function, x, would be equal to the root of the nth root of y. We would assume that y is positive. So even if n is even, we would always have a solution. So what would we do? Let us start from the simplest case. We'll start from n equal to 2, and we'll construct square roots using Q. So square roots. What should we do? First of all, let us define a function which performs, in this case, obviously, f of x is x squared minus y, and f prime of x is simply 2 times x. In this case, we would have xi equals to xi minus 1 minus x squared minus y divided by, oh, sorry, 2 times x. It was not 2 times y. You didn't stop me. Divided by 2 times x. So, initially, just to try it out, let's compute the square root of 2, probably. The first iteration, what would it do? We construct the following function. So let's say we need x0. Say x0 would be, let's say 1. We start at 1. So it doesn't need to be greater than the root. Then what we do? We do x0 minus precisely what we had, x0 times x0 x0 times x0 minus, in this case, let's say y is 2. Initially, we're constructing the square root of 2. Okay. Let us check. So 0 minus square. divided by the way, divided by, be careful, because if we do just slash, it is not a division. This is the adverb in Q, you remember, which lifts a function to a fold accumulating function. So instead of using the slash, division is actually given by the percent, very much like, well, the remainder is a percent in C++. In this case, it is a division. 2 times x 0. Okay. We got 1.5. And if we consider, so that the first approximation this method would give us for the square root. Again, let's derive a function which gives us a sequence. So we would say taking x I, we would a function with one argument xi, and the function will return xi minus square of xi, sorry, xi times xi minus 2 divided by 2 times xi. Actually, the second level of parentheses is not really necessary, but we'll use it. Okay, so taking this function and applying this function to the initial approximation, which is 1.0. It's interesting whether it would work if we apply it without brackets. Yes. If we then apply it to 1.5, we got already a better one. If we then apply, you see we're already pretty close. If we apply it to this value, we get even more close, and so on. 1.414 are already 3 valid digits. Then we would of course like to apply this function until it converges. And then obviously this adverb slash is to our help as well. So what we simply do, we take this function and apply it repeatedly until convergence to 1.5. Let me see whether it would be sufficient to do so without any further brackets, so maybe not. Not quite. In this case, we do need brackets. Okay, no problem. Then the root. Only the question is, oh, sorry. I have forgotten to apply. It is just the first iteration. I have forgotten to apply to, the root is not quite correct, to apply the adverb so that it would operate ad infinitum. Oh, here we are. We got the correct root. By the way, the actual value is very close to what we have obtained only after actually 3 iterations. That's the square root of 2. So you see, the whole loop which applies these Newton's iterations until they converge can be implemented in a single line. My question to you, so what are the convergence criteria? In our numerical implementations, if we do it using an explicit loop, for example, in Java, then we need to keep track of xi minus 1 and xi, and obviously we would run this until the absolute value of xi minus xi minus 1 would not become less than some given epsilon, all right? But what is the convergence criterion in Q? Well, the Q runtime system has some reasonable value. In this case, I believe that the convergence is decided when the absolute difference between the iterations is less than 10 to power minus 14. That's the value of epsilon in this case. And that's all. So the whole loop, which would otherwise require several lines, to say the least, in our favorite procedural object-oriented programming language, can just be done in one loop, in one line without any explicit recursion even, just using the adverb operation, lifting the function to repeated applications of itself in Q. Wonderful, isn't it? Now, let us, okay, we only constructed the square root of 2 in this case. So let us construct a function which takes the square root of any number. In this case, it needs to be a function of 2 arguments. So the first would be the value from which we extract the square root, and the other one is our xi. Function applied to the first argument is obviously the first argument, just a second. So the first argument is the value of the argument. So let's say it is to be applied to 10 first. I don't know whether we need this. And then repeatedly applying it to itself, starting from the initial value that's because it is still 2 rather than y. So it is still doing the same thing. But if we replace 2 with y and apply it, then we got the square root of 10. Although arguably this becomes a little bit tedious. So what we can even do, we can construct the root of any other nth degree instead of 2. But in that case, we would need to perform, instead of the square, we would need to perform n multiplications in order to raise our x to the power n, and n minus 1 multiplication, so the derivative would be equal to obviously n times x to the power n minus 1 if we to perform further multiplications in the derivative. Actually, why not? Let's do that. So suppose that p is our power. So the first argument is power. So for example, we'll compute the cubic root. The second one is y, the argument from which we take the root. The next argument is the current xi. What we do? We do xi minus. Now it is something, instead of doing xi times xi, we need to multiply xi over itself p times. We do it again by lifting our operation, so it is multiplication lifted. Taking p elements of the list consisting of only xi element of minus y divided by, now same for the power p minus 1. So first of all, it is p times xi power p minus 1, p times lifting multiplication and applying to p minus 1 repeated elements of the value xi. Okay. Now, sorry, I think I missed, and this becomes tedious, as you can see. I missed one bracket, which would backfire on me here. Then divided by this one. Oh, I think we are done. And now we would have, for p, I want a cubic cubic root. For the value, I would like to have 2, so it is a cubic root of 2. Repeated ad infinitum until convergence, starting from the initial point 1.0. Fire. That's the cubic root of 2. Don't you believe it? Multiplied by itself is 2. Yes. Now we know that cubic root of 2 with a very high accuracy is simply 1.26. Okay, we'll know. Okay, so no loops. We can do this. Okay. Now we are really moving into, from numerical applications of Q, we are moving into some kind of financial application. So for example, we are implementing a matching engine using the Q. By the way, implementing a matching engine in a database is not a so stupid idea. Do you know what the matching engine is? Maybe I mentioned it in the previous lecture, maybe not. Are you familiar with the exchange-based financial trading? No? Okay, I'll explain in a second. So the financial exchange is organized in the following way. For those who do not know what the financial exchange is, in the Russian it is called birja. Financial exchange. We trade a certain financial asset, so for example, a stock equity. And there are market participants at the exchange who want to sell some stocks. So for example, there is a certain stock and currently there are people selling it. Someone is selling just one stock and would like to get $100 for the stock. Other people, someone else, or maybe 2 more people, are selling same stock, one person 2 stocks, another person 3 stocks, but they want to ask a higher price, 101. Yet another person sells, for example, 6, but at a higher price, a yet higher price, 102, and so on. So this is a part of the order book. So they submitted orders to sell, and they request for the quantities available. One has one stock, another one two stocks, three stocks, and so on. They require the corresponding prices. So this is called ask side. Ask side represents sellers, those who would like to sell. There is also a bid side, which represents those who would like to buy. But you know, if you sell, you would like to sell high, as expensive as possible. If you buy, you would like to buy cheap. And for that reason, currently, the bidders or buyers, they do not want to pay $100 for the stock. The highest price one would like to pay, and he would like to buy 3 stocks, but only at the price of $98. There are some other people, yet another one is buying 5 and yet another one is buying 1, but they only want to pay $97. So obviously, if it continues like this, then no trades, no transactions would occur at all at the exchange. This whole structure is called order book. So there are orders to sell, which are placed at the ask side. There are orders to buy, which are placed at the bid side, and they stand in the queue, and no one trades actually, because no bidders would like to buy more expensively than at 98, but no one would like to sell more cheap than 100. And then a very useful person occurs. He is called aggressor or taker. He says, okay, I need a stock now. Really now. I can't wait until anything happens. So because I need it now, I agree to buy at 100, at the lowest price the seller offers. And then the trade would occur at the price 100 because he agrees to buy at 100. An order, a buy order for 100 would not even be placed in the order book, because this order immediately matches the lowest price on the sell side. And this match of the incoming order buy 100, buy 1 at the price 100, it immediately matches this order, producing a trade at the price 100. If this person needs 2 stocks at the price 100, then he would get 1 at the price 100, but there is no other one at the price 100. That's all. There was only 1 stock at the price 100. It is taken. That's why aggressors are also called takers. They take orders which are already placed in the order book and which were standing there waiting for the aggressors to come. But another one at the price 100 would become unfilled. What happens in this case is that the order book changes. So those 6 orders at 102 remain. Those 2 and 3 orders at 101 remain. But now the highest bid is going to be this unfilled order at the price 100. So here there is 1 at the price 100, and only below there are 3 at the price 98, and only below there are remaining 5 and 1 at the price 97, and all those below. So as a result of this trade, the lowest the lowest hanging fruit, the lowest order at the price 100 was taken, but the other one was unfilled and it is now standing on the bid side. So the order book as it was here is transformed to the order book as it now stands here. If this person needs to fill the second order to buy yet another stock, then he wouldn't be able to stay at 100. He needs to increase the price once again from 100 to 101, and in this case it would match one of the two orders, well, one of the orders available at the price 101. So what we would like to do, we would like to, and the computing machinery which perform these operations is called precisely the matching engine. So let's implement a very, very simple matching engine functionality in our queue. So what we will do, we will probably, let's do it other way around. So suppose that there are some bits. So I would say there are bits, and those bits starting from the best bid. So there are brackets are not needed, as you remember. Let's say 2, 1, I don't know, 4, 3, 5, 4, something like this. So these are bits. Okay. Now a seller comes, and the seller sells maybe 12 stocks. What will happen with the bits as a result? So basically, and he sells at, let's say, so-called market price. So the price doesn't matter in this case. He sells and matches with our orders on the bid side until the whole amount of bits is exhausted. So what will happen? The first, irrespective to the price, because in this case he's prepared to sell at any price actually. First of all, he sells out of 12. He sells 2 to the first one, then 1 to the second, then 4 to the third one, that's already 7, then 3 to yet another one, and then it's already 10, and then only 2 remain to be sold. So those who wanted to buy 5 only gets 2, and 3 remain unfilled. And the person who wanted to buy 4 in this sequence is not filled at all and will have to wait. So how would we do it? How would we do it? I propose okay, let's make a very short break and we'll complete this example, just 3 minutes to rest before we go into implementation of a matching engine. Okay, we're back. So what do we do here? Basically, what we need to do is simply to construct a running sum of our bits and then cap this sum at the value to sell. You remember there was a function sum which was the same as a fold running on plus, but there is also a version of this function which provides a list of cumulative sums. So for example, we can do sums we can do sums of let's say sums of our bits 2, 3, 7 and so on, and you see that really the fifth one would be kept at 12 because there are no more to sell than 12. So then we would say if 12 let's say sell is 12, then we can simply cap using the maximum our amount.
Sorry, can you please turn on the screen sharing?
Is it not on? Just a second. Apologies if not. Just a second. Yes. Okay. So capping so we see the first four bits are completely filled. The final one is not completely filled. Now, if we want to see the actual amount of fills, we apply yet another built-in function in Q, which is called delta. So first of all, you see we do a running sum, then cap this running sum by the amount to be sold, and then compute again the deltas of the running sum to see the exact amount to be sold. No brackets are necessary in this case because everything is evaluated from right to left. So now you see the first bidder really buys 2. The second one, so the full amount is filled. The third one is also filled. The fourth one is filled. The fifth one is partly filled. There is such a term as a part. Only buying 2, whereas he wanted to buy 5. And the other one is not filled at all, buying 0 instead of 4. That's a very simple operation of a matching engine inside the queue. By the way, you might ask me, okay, we're talking about the queue language, but where is the database here? All data structures we currently deal with so far, these were actually lists. They can be backed by a persistent storage by the database engine completely transparently. So it is the queue language which is important in this case, providing either evaluation in just the in-memory space or evaluation backed by database storage if you configure it accordingly. I'm not discussing how to configure. The persistence. I'm discussing really the properties of the functional Q language, which is at the heart of the KDB plus Q time series database. And finally, we introduce, I'll probably take 10 more minutes of your time, because that's, I would say, quite important. And we finally introduce yet another, along with lists, extremely important data structure in Q, which is obviously a dictionary. So a dictionary is simply a map between the set of keys, and the keys are typically symbolic. You remember strings or atoms are symbols prefixed with the tick, and some values. Now, from your theoretical computer science, you probably have seen, you remember what the associative list is. It is a list of pairs. That's how a dictionary can be constructed. It is constructed by zipping or associating two lists of two elements. So for example, you will guess what we get here. Take keys A, B, and C. No spaces is required. This is a list of keys. A map constructing operator, which is the exclamation mark, and then some values, 10, 20, 30, for example. That's precisely a dictionary or a map. Clear? Okay. We can obviously assign some values. So for example, dict is assigned a value which is precisely this. Now, we can do the following. Well, that's a very simple dictionary. We can consider a slightly more complex one, where the data are stored column-wise. The column-oriented databases I was talking about, they come into play here. So what does it mean? It means that A, B, C are now names of our columns, and the values are not elementary ones. The values are lists. So the following is a column-oriented data storage or a column dictionary. So let's call it CD, column-oriented dictionary, is, let me do just two columns, A and B, mapped to just anything we can think about. So suppose that the first one is, let's say, a list till here I think we need brackets. The first one is a list till 10, and the other one is 2 minus till 10. Obviously, they need to be of equal length. Okay. Yes, they are printed as rows, but in fact they are columns in this case. So you can extract the whole value of a column if you use the key in bracket notation. So that's the first one, and in a similar way, the second one. Now, this is a column-based view. What we would also like to do is to get a traditional row-based representation, which would allow us to provide a row-oriented view. In this case, we need to transpose, or let's say flip, rows and columns in our representation. There is a built-in flip operator in Q. So let's construct out of this column-based representation, let's construct a table. So a table would be, let's say it is called T. It is simply a flip operation applied to our column-oriented database CD. What do we get for T? We got a very traditional database table representation, right? Very much familiar to you with like any output of, let's say, scale select or anything like that. That's a table. But what's interesting is that this flip only changes the view. The original representation is still a column-based one. It is still actually a map from the keys to two lists of integers represented column-wise. Flip only provides a way of viewing, remember views in SQL, or indexing or accessing this database. So this is a table, and actually this is a built-in first-class entity, a built-in Q data type, which is a view, table-like view on a column-oriented data storage. And then obviously you can do standard database operations. So for example, there is even QSQL, SQL-like language built into Q. So something like the following should probably work. Select from T we have constructed. Yes. Select. You remember our columns are called A and B. Select now without ticks. Select A plus B from T. Here we are. So it is indeed a query language and a processing language for a column-oriented database suitable for storing. This remains to be seen. I encourage you to try to store large amounts of data and implement some computational logic over it. That's the foundations of Q programming language backed by KDB plus database. That's basically all I wanted to tell you today. Really go to kx.com, register, install a 64-bit preferably version of KDB on your local machine, which is only operational if you have a permanent internet connection. It wouldn't work when not connected to the internet to prevent abuse. And you will be able to play. There are a lot of learning material actually on the KX site. You will be able to play with KDB. This is an important thing. A good, experienced, highly skilled KDB Q developer can become a consultant for, let's say, a London-based investment bank and get £1,000 a day before tax. These are typical consultancy rates for KDB plus professionals. Sounds encouraging. And by the way, there are positions for KDB plus in Russia as well. Very recently, I would be disclosing some open secret in this case, is that a certain, as it stands, a certain high-profile Russian financial exchange is now moving its database technology to KDB plus Q. But there is only one high-profile, high-performance Russian exchange. Guess what? It is the Moscow exchange. So as far as I understand, it is the Moscow exchange which is now going to hire KDB Q consultants. There is a very good incentive to learn more about KDB and Q and matching engines and how the financial trading operates in general. And on this optimistic note, I would like to conclude our database module of this academic year. Thank you very much. Any questions, please?
So how exactly this KDB plus Q is used on stock exchange? So they are dumping like some data and after this process it and analyze, or what?
There are two ways of how it can be done. In the Moscow exchange, I believe, yes, for data storage, because the exchange is legally obliged not only to match orders, but to keep track of all events which have occurred within the exchange. So, for example, any submission of a new order which was placed somewhere in the order book, maybe it was never filled, then cancelled, but it needs to be recorded. Obviously, all trades, all order cancellations, absolutely everything, which results in a huge amount of data per day. If you look, for example, at the most liquid instruments like USD ruble or Euro ruble currency pairs at the Moscow exchange, then an order book update occurs every 1 millisecond on average. And the exchange is open from 10 a.m. to 23:50 in the evening, which makes it roughly 49,000 seconds, or 50,000 seconds, something like that. So it is 50 million updates only per one instrument a day. And if we say liquid instruments of that scale, maybe let's say 4 instruments in the FX asset class, Euro ruble and USD ruble with the delivery of today and tomorrow, so that makes 4. At least 2-3 very liquid futures in the futures section, futures on the Euro ruble, USD ruble, maybe Euro ruble, maybe on the exchange index itself, maybe some others, plus a few liquid equities. Say multiply this by 10, this means 500 million updates per day. Each update is at least originator ID, price, quantity, and so on. So it would be 100 bytes, something like that. So it's 5 to 10 to the power 8 times 100, which is 50 gigabytes of data a day. But I think, in fact, it is much, much more than that. So probably 100 gig of data. And then you need to perform extensive search operations on this data. So for example, you need to, when a trade occurs at the exchange, it is not a trade. It is just an indication of the trade, that 2 orders matched. No money transactions would occur at that time. Only when the trading is over, so for example, after a particular cutoff time, all trades are collected and the actual money transfers occur between the parties involved. If I got from you a stock for $100, I bought it from you, and then I sold it back, and it happened that I sold it back to the same party, to you, at 101, then there is no need to execute these two monetary transfers. What really happens is, as a result, only $1 goes from you to me as a result, because I bought at 100 and I sold to the same party at 101. Therefore, all these transactions need to be collected, netted, to eliminate mutually matching transactions, and then the residual amounts of money need to be transferred between the accounts of the exchange participants. This process is called clearing. Clearing at the end of, or settlement, at the end of the trading day. This is a relatively computation involved procedure, which in the past would take maybe 15 minutes, maybe more, and needs to be run in parallel for multiple instruments. So it is a significant computational stress. So I believe that the first good application of KDB plus technology would be to significantly speed up the settlement process, and maybe to allow more frequent intraday settlements as opposed just to one after-day settlement as it used to be in the past. Plus various intelligence operations, for example, to detect market manipulation attempts, placing orders without the intent to fill them. This is a very well-known illegal market manipulation technique. Maybe some others, in order to enforce rules and regulations about the exchange trading. So that's how I believe the best promising application for KDB Plus and the Moscow exchange would look like. At a smaller scale exchange, you may even implement the whole matching engine in Q. By the way, it has network interfaces, so you can do network IO sockets, whatever, and then you use KDB plus Q as just fail-safe, fail-proof matching engine backed by persistent storage. It's probably not for the Moscow exchange because the performance limitations would still be too strict in this case, but for small exchanges like crypto exchanges, this might be a very good option to implement the entire matching engine in Q. So like that.
Thank you.
Any other questions, please? If not, then we are done. You will have an exam very soon, on Monday, right?
Yes, on Monday.
And believe me, there will be questions on KDB. So please take it seriously. Thank you.